Hello, welcome back to this last set of videos. This will be video number 4, video 4 for the week of April 20th. All right, and last video we looked at for comprehensions. This is a neat syntactic structure in functional programming in general and in particular in Scala. Okay. So, and the last example we did was the pair of numbers, each number being less than 7 and more than 0, such that the second number is less than the first number, and the sum of the two numbers is prime, right? So that example was nicely captured in this piece of code, small piece of code in the for comprehension here. Okay. So we set something called the generators in the beginning. I is assigned 1 until n, so I would be an element of this range 1 through n, actually 1 through n minus 1 because of the until, and j will range from 1 to I, okay, so j will be one of the elements in that range, and this will automatically make sure that the numbers are in the proper ranges and j is less than I, and the next is called the filter, okay, this third line. So the first two are the generators, and this third line here inside this is the filter. And the filter syntax is if and then some condition. In this case, we call the is prime function we wrote earlier, and then provide I plus j as a parameter. And if that condition is true, we yield I comma j. So I comma j will be put in the output. The output is a sequence here, okay, and so we'll get a sequence of all the pairs which satisfy those conditions. All right, so it's a nice construct. Try practicing this in other situations, and one other place we can see it being used is the scalar product. Last time we saw that. See, you start with xs zip ys, so this will give you all the pairs from the two vectors, and by putting this generator, we instantiate any one of them by x comma y, any one of the pairs. Okay. And then we yield x times y, so it will be the product of those two corresponding numbers. And because this for comprehension works over the whole, all of the items in the generators, you'll get all the products in a sequence. Okay, and then take this whole expression, which is starting here and ending there, will be the sequence of the products. Okay, and then you do a sum on that, and you get the scalar product. Okay. All right, so that's for comprehensions. Now we're going to learn two more data structures, or built-in structures. One is called the set, and the other is called the map, okay, or the dictionary. So let's look at the sets. Sets is another basic abstraction in the Scala collection. Little different than the sequence, because here duplicates are not allowed, and the order of the elements are not specific. I mean, they could be random, right? So sets. So this is how you define a set, use the keyword or the class set, and then provide initial values for the set. Okay, so val fruit equals set of that. And then, of course, you can use the contains method, which I guess comes a little bit later, okay, to check for membership. Okay, and you can also convert the set into a list and then use the list operators on that if you want. Okay. Now here, in the next two lines, in the next line especially, we have a sequence, 1 to 6, right? So that will be 1, 2, 3, 4, 5, 6, a sequence, ordered sequence, okay? You can convert sequences to sets, okay? Dot to set, and then you'll get the set 1, 2, 3, 4, 5, 6, okay? And you can see here in the result, the set S is 1, 2, 3, 4, 5, 6, but suddenly the order has mixed up, okay? The order is not relevant inside a set, so that's why it probably created a hash set and then internally represented them some way. Okay. The third one is a range, 5 to 9. Not even sure why that's present here, but that's just a range. It's not a set. Okay. All right. And most operations on sequences are also available on sets. Okay. So for example, if s dot, the same set above there, 1 to 6. Okay. S dot map underscore plus 2. Now this again is a short notation for if you're not still used to this, this is the x plus 2, okay? So that's the function which is denoted by underscore plus 2. Okay, so remember, if you had a certain number of parameters and they appear exactly once in the body or of this function, anonymous function, then we don't have to write this front part. We can just put underscores in the places where the parameters appear. Okay, so we could do s.map underscore plus 2 or this function here, same thing. And for the 1 to 6, this hash set, right? So that's what S is. Okay, you'll see that 1 will be added to each one of these. Excuse me, 2 will be added to each one of these. You'll get 7, 2, 8, 4, 5, and 6. Okay, but the sums don't appear in the same order. So you can actually see again the plus 2 also got mixed up here. But we do get the same answer with a set in which every element has been added by 2. Okay, increased by 2. And the next one, the filter here. Okay, let me run this cell because there is only 3 answers for 4 expressions. Oh, S not found. Okay, so I guess this happens once in a while inside Jupyter Notebook. Okay, I probably need that value here. Okay, fruit. Oh, I guess we had to do the same thing for the fruit as well. Okay. Okay, I got the S and the fruit defined here, and you can see that these two here, the maps, s.maps, both are the same answers, 5, 6, 7. Okay, and then the fruit filter, you can actually apply filter functions. Okay, on a set. Okay, and here we are applying underscore dot starts with app. Okay, so this is again the same as x arrow x dot starts with app. Okay. I will not repeat that expression here. Okay, so this will go through all the items, and then anything which begins with app, it'll include in the answer. Okay, and that's what that is. So the filter takes place on each of the items in the set. Okay, so the map, filter, reduce, and all those things will be applicable here as well. Okay, and the main differences between the sets and sequences are sets are unordered. Sets do not have duplicates, and the fundamental operation in the set is a contains. Okay, contains is a membership check. Okay, so here is an example S and T previously. Okay, I think it's from the previous. I'm not sure. Okay, let's see what happens here. T. I'm not sure if we define T up there. Probably here. Yeah, maybe we need to bring that down into this. Okay. Yep, and that's that, and let's go back here. Okay, so we have the S and the T. S was the number 1 through 6, and T was the numbers 5 through 9. Okay, so S is 1 through 6, T is 5 through 9. Okay, so S contains 6 will be true, and this also should be true, I think so, right? S contains 8 should be false because it stops at 6. Okay, so true and false. And then the S plus plus T, this is the concatenation or putting them together. So you should be able to put two, just like you can put 2 lists together, you can put 2 sets together, and the union of these 2 will be there. And of course, duplicates will be removed. Okay. All right. So that's sets. A very quick introduction to sets. So we know sets, we know lists, we know arrays, we know vectors, and we know ranges. Okay. So those are 5 important built-in data structures available in Scala. All right, the next is to solve the n queens problem. Okay, and I'm not sure if you're familiar with the chess n queens problem. So you have a chessboard, given a chessboard n by n. Okay, so it's a square chessboard, and we want to place n queens, 1 per row or 1 per column, so that none of them are attacked by any of the other queens. Okay, and queens can attack other queens by being in the same row or being in the same column or diagonally. You see, that is, if they're in the same diagonal, then one queen can be attacking the other queen. Okay, so we do want to place the n queens in the board so that none of the queens are attacking each other. Okay, interesting problem. Now this is a classic problem in search spaces. This is actually a NP. It's a hard problem in the sense that time complexity is exponential. Okay, but what we do is we typically use a backtracking algorithm to solve this problem. Okay, so that is, you place one coin in the first row. Okay, and then you try all possibilities for the second coin in the second row, and if you find a position where there's an attack, then you try another possibility, right? So try a possibility and place it there. Okay, and so on. And if at some point in time you don't find a possibility, then you go back to the previous step and try other possibilities there. Okay, so in the worst case, you'll have to try all possibilities, which is exponential. Okay, anyway, we will use some similar solution here, okay, in Scala. And the general algorithm is as follows here, these two lines here. Recursively solve k minus 1 coins. Okay, so suppose you have to solve for k coins. Okay, then you recursively solve for k minus 1 coins. That's the magic of recursion. Okay, so you get immediately most of the solution. Okay, so the recursive call will give you the solution for k minus 1 coin. So you'll have a board with k minus 1 rows solved. Okay, that is 0, 1, row, whatever, row 1, row 2, row 3, up to row k minus 1. Okay, and the last row is what you need to solve. That is, you need to place the kth coin, and the second step is place the kth coin such that it is not attacked by any other previous coins. All right, so this is the algorithm. Okay, but it's a recursive algorithm. Okay, and we want to implement that. Okay, algorithm looks relatively straightforward and simplistic, right? Just 2 steps. So let's go and do that. Okay. Okay, we need some data types here. Okay, because it's a square board, we have rows and columns, right? So the position of a coin, let's call that a type coin, will be a pair of integers, right? So for example, 0, 0 would be row 0, column 0. Okay, so this first one is the row, the second one is a column. Okay, and a pair like this would designate one of the cells in the, or one of the squares within the large square. Okay, row, column. Okay, so this will be used for row, and the second one will be used for column. That's a location of a particular coin. Okay, now in general, the solution, even though we are asking for one solution to this problem, okay, so place, but in general, if you study this problem in detail, you will realize that there are many solutions. You see, there are many ways you can solve this, many solutions. That is, there's not exactly one answer for this. Okay, got it? So we do want to generate all the solutions. So this problem is stated in such a way that generate all the solutions. Okay. Now, how will a solution look like? A single solution look like? It'll look like, because it'll be positions of coins, right? So it'll be like this: a list of coin, correct? List of pairs of integers. So that's the data type of a solution, the list of coin. And a list of coin will be the data type of all the solutions. Okay, so it'll be a list of solutions, correct? So and a single solution is list bracket coin. Okay, so that's what we're going to work with, these 2 data types. Okay, but before we get to that, I just want to illustrate this with a small toy example, just the idea of what's happening. Okay, so let's take n equals 4. Okay, so it's a 4 by 4 square. You can see here, down here. Okay, and the rows are labeled 0, 1, 2, and 3. Okay, so the rows start at 0 and then end at k minus 1 or n minus 1. Okay, so in this case n is 4, so the last row would be 3. Okay, and similarly the last column will be 3, so the columns are also labeled 0, 1, 2, 3. Oh, ignore that line. When I was drawing this picture, that line showed up. Okay, all right, so we have a 4 by 4 chessboard. Okay, and let's say that k minus 1 would be 3, right? So let's say that the problem has been solved for 3 coins. How? Don't ask. Okay, this is given to you in the recursive solution. Okay, so let's say that this is one of the solutions. Actually, there can be many solutions, but let's say this is one of the solutions here, down here. Okay, that is, we already have a solution, one solution, a single solution, which is a list consists of 0, 2, 1, 0, and 2, 3. Okay, so 0, 2 corresponds to this coin, 1, 0 corresponds to this coin, and 2, 3 corresponds to that coin. So those are the three positions of the queens we already have determined, let's say. Okay, this is recursive, magic you get from recursion. Okay, so in recursively you got this solution. Okay, now you might get other solutions too, so we'll have to do the same analysis on the other solutions as well for 3. Okay, now we had to place the fourth queen, right? So that's the second step. Find the recursive solution and place the last queen. Okay, so now these are the 4 positions you can place the queen in, right? 3 0, 3 1, 3 2, 3 3. So these are the 4 positions we can place the fourth queen. Okay, in row number 3. Okay, but before, actually not before, while we are placing these, we also have to verify whether that particular placement has been attacked by any of the other queens. Okay, and of course you have to verify that, and then if it is attacked, then that won't work. You go to the next one and so on. Okay, so you'll have to try each one of these, one at a time. Okay, so 3 0 here, no, right, because that's attacked by that queen. 3 1 here, yes, it works. Okay, so you actually don't have to go to the others unless you're generating all solutions. Then you have to go to check the others. But actually in this case, the other 2 are not valid positions because they're attacked by those 2 queens. So 3 1 is the correct solution, so you would get that. Okay, so you would place that here. Okay, so that's the idea. So you will recursively solve for k minus 1 queens, and then the kth queen you'll place one at a time exhaustively in each of the positions and verify if the this kth queen is being attacked or not. Okay, and if it is attacked, then you go to the next option. If it's not attacked, you're done. Okay, so that's the general idea. Okay, so here's the full solution. Yeah, I think I can. Yeah, actually a little bit. Maybe I can increase this. Yep, I brought it down a little bit. Okay, so I think we can look at the whole. Yeah, sort of. I don't think we can see the queen sub 4, but let's forget about that. Okay, that's the main call. Okay, so let's look at everything else. Okay, so here's the solution. Okay, so we have the 2 types defined above: queen, int, and solutions list of queen. Okay, so we got the 2 types, and here's our main function def queens, and it takes n, the size of the board, as input, and then returns the answer. Okay, here, this is the answer. Okay, it's got 3 helper functions. One is called attacked. Let's look at each one of these 3 separately. Okay, let's look at attacked. Attacked, what it does is that it takes 2 queen positions. Okay, Q1 and Q2. These are 2 positions on the board. Okay, so we can assume the rest of the board is empty, and these are the only 2 queens placed there. Okay, and what this will say is that it will return true if Q1 attacks Q2. And by the way, this is a commutative property. If Q1 attacks Q2, Q2 also attacks Q1, right? In an attack scenario, both can attack each other. It's only the matter of whose turn it is that person wins, okay, or that queen wins. Okay, so this will return true if Q1 attacks Q2, okay, and false otherwise. Okay, and how do we check this? Okay, I think if you understand this board, you would quickly realize that 2 queens in the same row would not work, right? They can attack each other. Also the same column, and that's what these 2 do. So the first condition is they're in the same row. Okay, Q1._1 equals Q2._1, same row. Okay, right, because the first of the 2 integers in the pair is the row, and second one is the same column, Q1._2 equals Q2. So if they're in the same row or in the same column, or you see that I don't have an if then else. Okay, that's because this whole Boolean value itself is the answer. Okay, so either they're in the same row or in the same column, or they're on the diagonal. Okay, that is they fall on the same diagonal. Okay, and if you do a little bit of math, you'll see that the 2 queens are in the same diagonal if the absolute value of the difference of the rows equals the absolute value of the difference of the columns. Okay, you can do this math yourself. Okay, take 2 queens on the diagonal. Okay, and then look at the rows and the column numbers and subtract the row numbers and subtract the column numbers. You'll see they're the same. Okay. Okay, so this condition checks whether 2 queens are in the same diagonal. Okay, and these are the only 3 ways they can attack each other, right? So if it's either this or this or this, true. If any one of them is false, then if all 3 are false, then it's false, right? Then false attack means it is not being attacked. Okay, so it's a very simple logic here on row number, column number, and the diagonal. Okay, so that's the attacked helper function here. Okay, there's another one called isSafe. Okay, this is not just checking for one coin versus another coin, which is what the attacked did, but isSafe checks whether one coin position is safe to place compared to all other coins which are already there on the board. Okay, so the others would be all the other coins on the board, this one. Okay, and of course it will be in the form of a list of coin. It's a partial solution in some sense, and this is the new coin we are placing. Okay, so we want to check whether it's safe to place this new coin on a board where the others are already present. Okay, and if it's safe, then Boolean true, otherwise false. Okay, all right, and here's a very simple condition to check for that. Okay, so you do a for all check. Remember, we just saw the for all check. Okay, so others is a list, right? And for all means this condition which is written on the right side must be true for every item inside this others. Okay, and what is that condition? X, this is a function, predicate, anonymous predicate. X would be one of the values in the others. X, for each of the X, it should not be attacked by this coin. Okay, if that's the case, if none of the others are attacked by this queen, then this queen can be placed where it is supposed to be, where it is. Okay, right? So that's a very simple for all check to make sure that it is not being attacked by any of the other queens already on the board. Okay, so this others would be all the queens already on the board, and this queen will be the new queen which is being added in the next row. Okay, in the kth row. So this is for k minus 1 rows and k. So those are the two helper functions, and now we are ready to write the main helper function, which is place queens. It's a recursive function, so that's why we say k here and not n. And of course, we call place queens with n, which is the main parameter there. Okay. So now place queens, the way it works is it's going to be the recursive solution that we just discussed. Okay. So input is k integer, and output is solutions, which is it's going to collect all the solutions. Okay, not just one solution. So it'll print all the solutions. It starts with k equals 0, the base case. Okay, if that's the case, then we haven't even started, so we must create an empty list for solutions, right? Because we don't have a solution yet. This construct in the front of it, list of int, is basically the type of that list, nil. Okay, empty list. We have to. It's good to make that explicit here so that Scala knows what type of list solutions is. Okay, all right. It might be smart enough to figure this data type out on its own. Okay, but anyway, that's how we construct it. Okay, so if k is 0, then we have an empty list of solutions. Okay, there are no solutions found yet. Okay, and we're going to build on that in the else part. Else means k is at least 1, right? 1 or more. Okay, so we do a for comprehension. You can see that here. Okay, for, and these are the two generators. Okay, so first we do the recursive call, and we say place queens k minus 1. So we make the recursive call and get all the solutions for k minus 1. Okay, so these queens would be a list of solutions, and each solution is a list of coin positions, right? So queens is a list of solutions for k minus 1. Okay, that is if the size of the board was k minus 1. Okay, which means that each of the solutions and queens would contain. Oh, by the way, place solutions is the list of solutions, but because this is a generator, this queens will be one of those solutions. Okay, because in a generator on the left side of this arrow, backside arrow, we put a variable which denotes one of the values of the right hand side. Okay, so queens here will be a single solution. Place queens k minus 1 will be all the solutions. Okay, so that's with k minus 1. Okay, so queens is one particular solution for k minus 1. Okay, which is a list of queen positions in rows 0 to k minus 1. Okay, or 1, yeah, that's right, 0 to k minus 2 maybe. Okay, and then here is where we check for all the columns. Okay, so now we are going to go to the next row. Okay, the next row would be k minus 1, row number, right? Because if you had solved for k minus 1, then all the rows from 0 to k minus 2 have been filled up. Okay, so k minus 1 is not yet filled up. Okay, but for k minus 1 row, we have to check all the columns 0 to n. Okay, right? Because we have to keep checking each position in the last row, and as soon as you find one solution, you can stop. Okay, and this is the predicate or the filter. Okay, if is safe k minus 1 comma column, that will be the the next position to test, okay, for a queen, and if that is safe against the queens, the previous solution, okay, then we can yield k minus 1 column as a new position and attach it in front of queens. Got it? So this we found a new position. Now this whole for comprehension works for different values of queens and different values of column. Okay, different values of queens and different values of column. All right, different values of queens are the all the different solutions for k minus 1, and column is all the values for the columns 0 to n minus 1 actually, because it is until, okay, and it's going to check k minus 1 column and check whether it is in conflict with queens. If it is not in conflict and if it is safe, then we can add that position to in front of the queens. Okay, so this automatically checks all combinations of queens and calls and then gets you all the solutions later. Okay, here you go. Okay, you want to try to run this? Fingers crossed. Okay, some issue here. Okay, actually I did find this issue for some reason or the other. I wonder what that was. Okay, let me try without the type there. Okay, I guess I shouldn't have pressed that. Yeah, I remember spending a few minutes, but I didn't make any significant changes actually. The solution was working as it is. Nil, okay. Oh, okay, I know why, okay. I know why, okay, because remember we had this BST, where maybe that's what is causing. So let's make a just that. Now we do want an empty list here, okay. Yeah, that is a problem. Okay, you remember NIL we used a bit earlier in the when we were discussing the binary search tree. So that NIL and then this NIL was conflicting, okay, and that's why we had a problem. Okay, anyway, this is another way to write an empty list. Okay, so it does work, and you can see there are two solutions. Okay, actually the second one is what I think I wrote earlier, but to this 4 n equals 4, these are the two solutions for the placing the queens. Okay. All right, I think maybe we should stop a little early here because the last topic is Scala maps, and I'd like to do that in the final video. Okay, thank you.